Welcome to the Deep Dive. This is where we take the sources you send our way, all that dense information, and really try to turn it into actionable knowledge for you.
Exactly.
Today we're plunging into something pretty fascinating. It's a collision, really, between the past and the present.
Mm-hmm.
We've got this classical, century-old engineering mechanics problem. Think stresses in materials.
Right. Fundamental stuff.
And it's running headfirst into a fundamental breakdown inside modern, very sophisticated software.
Yeah, our mission today is kind of zeroing in on this thing called the Boussinesq solution. It's a cornerstone, goes back to 19th century physics.
Okay.
It defines how stress and forces distribute in elastic materials. So think about soil settling under a huge building foundation, that kind of thing.
Right, I can picture that.
And a listener shared sources detailing this issue, where the method of calculation, it actually depends on which software version you're using.
Mm-hmm.
It produces mathematically incompatible results.
And that's the hook, isn't it? We're not talking tiny rounding errors or, small numerical differences.
Not at all.
We're talking about expensive, specialized software that's failing to uphold, the most basic rules of calculus, algebra even.
It's pretty shocking.
Run the same calculation on two different versions of the same product, and you get two symbolically distinct, non-equivalent mathematical answers.
Yeah, this is a really profound issue. So the Boussinesq solution, it describes the action of a single concentrated force. Imagine poking an infinitely large block of jelly, basically.
A half space.
Right, half space, exactly. And we use this solution as what's called the green function.
Green function? Explain that a bit.
Sure. Think of it like dropping a single pebble into a pond. The green function is like understanding the ripple pattern from that one pebble.
Ah, okay.
If you get that, then you can figure out the overall wave pattern if you toss in a whole handful of pebbles or rocks.
So the Boussinesq solution is the pebble, the fundamental ripple. And we use that to build up solutions for real-world problems.
Precisely. Like calculating how much a rectangular foundation slab will settle when you put a uniform load on it.
Which brings us neatly to the classical foundation of this whole issue.
Exactly. Historically, finding these perfect, exact solutions in elasticity theory is, it's nearly impossible unless the shape, the geometry is super simple, like a half space.
Right.
So our sources, they focus on a key historical investigation. It's often called the Love problem.
The Love problem.
Yeah, formalized by A.E.H. Love back in 1929, though it built on earlier work by Schleicher in 1926. The problem is basically calculate the vertical displacement, the sinking, and the stress under a rectangular area with uniform pressure on it.
Okay, let's unpack that. The power of using this green function, this Boussinesq pebble, is that it lets you get an analytical and exact solution for these displacements, right?
Theoretically, yes. That's the beauty of it.
But the sources are saying that even getting to that solution in a modern computer environment is tricky. Where did the first roadblock show up?
It showed up when researchers tried to calculate the definite integral, the integral with specific start and end points.
Okay.
So when solving for that vertical displacement, let's call it W, for a uniform load over just a simple square, the authors found that if they just asked Wolfram Mathematica, this software, to calculate that definite integral directly, even simplifying things by looking right at the surface, the software often just choked, failed completely, couldn't return a result.
It just stalls. Why is that failure significant? I mean, couldn't it just need more processing power or something?
Well, it suggests a deeper issue. A fundamental limitation may be in the symbolic engine when you give it those definite bounds. See, asking for the definite integral means you're asking it to do the integration and simplify the result within those limits all the time.
Okay.
And the authors realized, hey, to get the known established answer, the one Schleicher figured out nearly 100 years ago, they had to use a workaround.
And that workaround involved the indefinite integral first, is that it?
Exactly. You got it.
Right.
They had to first solve for the general mathematical expression, the indefinite integral, without the specific limits. And then, only after getting that general formula, could they manually substitute in the specific start and end points for their rectangle.
The fact that you even need that two-step process in modern software, that feels like a warning sign already.
It is. It really shows the symbolic solver struggles with the complexity of this green function when boundary conditions are applied right from the start.
So, okay, the workaround exists,
yeah,
but the very need for it, calculating the indefinite integral first, that actually became the key, the diagnostic tool.
Precisely.
And what it uncovered is the real shocker here. the software's ability to handle that indefinite integral consistently. It changes dramatically just based on the version number you happen to have installed.
Yeah, this is where the whole deep dive pivots.
Yeah.
The software versions produce different symbolic answers for the same indefinite integral. We're not talking numbers here. We're talking about the actual mathematical formula being different. A failure in the symbolic integration algorithms themselves.
Wow. Okay, so how did they pin this down? How do you test the symbolic engine itself?
They used a really clever, simple test based on, like, the most fundamental rule of calculus you learn in first year.
Which is?
The integral of a sum must equal the sum of the integrals. You know, f plus g dx has to equal f dx plus u co dx. Algebraically identical.
Okay, basic stuff. So they applied that.
They did. They took the really complex formula, the integrand describing the load, and they just mathematically split it into two parts, f and g. If the software is working correctly, integrating the whole thing at once, f plus g, should give exactly the same algebraic answer as integrating f, then integrating g, and then adding those two results together.
Right. It's like a self-consistency check for the software's math brain. Did they run this check across different versions?
Yeah. They tested 5 specific versions of Wolfram Mathematica, spanned about a decade of development. Versions 8.0, 11.3, 12.3, 13.3, and the latest at the time, 14.2.
And the results were inconsistent, you said.
Shockingly so. There was a clear divide.
Okay, lay it out for us. The scorecard. Which versions failed? Which ones betrayed that basic calculus rule?
The older versions, so 8.0, 11.3, and 12.3. They all failed the test.
Failed how?
When they compared the result of integrating the sum versus the sum of the separate integrals, the answers were not algebraically equivalent. There was always this leftover bit, a non-zero remainder. The authors called it a residuum.
A residuum. Sounds technical, but if the results aren't algebraically the same, that means the software is literally changing the mathematical structure of the solution, right? Depending on how you ask.
It's an algebraic mess.
Yeah.
It means those older versions were spitting out mathematically different forms of the solution based purely on how you structured the command.
Yeah.
Integrate all at once, or integrate in pieces first. Different answers.
That's not good. What about the newer versions? Any hope there?
Yes, thankfully. Versions 13.3 and the newest one they tested, 14.2, they passed with flying colors.
Okay.
In those versions, that fundamental calculus theorem was fulfilled. Integrating the whole thing gave the exact same algebraic result as summing the integrals of the parts.
So it seems like the developers probably figured this out and fixed it in the more recent releases?
That's the strong indication, yes. The underlying flaw seems to have been corrected.
Did the study get into the weeds on the why? What was the likely technical root cause for this symbolic mess in the older versions?
They did have a strong hypothesis. It seems to relate to how the software handles two closely related functions that pop up a lot in these elasticity problems. Specifically, logarithmic functions, ln x, and inverse hyperbolic tangent functions, arctan x.
Okay, ln and arctan, they look different, but they're related mathematically.
They are. They're mathematical cousins, actually. There's a specific identity connecting them.
Arctan hex is equal to 1/2 times the natural log of 1 plus x over 1x. I see. So maybe the software's internal simplification engine was using different forms of this relationship inconsistently.
That seems to be the crux of it. The study suggests that changes or inconsistencies in the symbolic integration algorithms, particularly in how they simplified expressions involving both ln and arctan, caused the internal logic in the older versions to kind of break.
Did they try forcing it, like manually replacing arctan with the log version?
They did try that substitution, yeah. But even doing that manually didn't resolve the discrepancy in those older faulty versions, which confirms the inconsistency was deeply embedded in how the software processed the expressions, not just a surface-level substitution issue.
Okay, let's pivot to the so what factor. What does this actually mean for an engineer on the ground?
Yeah, the practical consequences.
If you're using one of those older versions, maybe calculating settlement under a big structure, a dam or something, what happens because the software might give you two different formulas for the same problem?
Right, that's the key question. And that's where the risk assessment part comes in. Now, for most of the area you're calculating, say, the parts of the foundation far away from the center point, the difference between the correct result and the faulty one from the older software is actually pretty small.
Okay, so mostly negligible.
Mostly negligible, yeah. Probably wouldn't cause a major design error in those regions. You wouldn't lose sleep over it necessarily.
I sense a but coming. There has to be the critical spot. Otherwise, why are we talking about it?
There absolutely is. The sources show very clearly that the differences between the correct solution and the incorrect one from the older versions they become significant. And worse, they can even go to infinity right near the origin of the coordinate system. That's where x approaches 0 and y approaches 0.
Okay, wait. In real-world terms, if I'm modeling, say, a square foundation slab, the most intuitive place, the place everyone puts the origin of their grid, the zero point, is smack dab in the center, right?
Exactly. It's the natural reference point,
Yeah.
the bullseye.
And you're saying that specific spot is where the error in these older software versions blows up, potentially to infinity.
That is precisely the finding. And it's the absolute worst place for the error to occur when using those unreliable software versions.
So if you choose the center of the foundation as your origin, which seems logical,
you are calculating the displacement right at the point of maximum error. And if that error diverges towards infinity, the calculation for the most critical spot, the center, usually where the settlement is highest, is completely meaningless, worthless.
That is genuinely stunning. The one place where an engineer needs the most certainty, the point of maximum expected settlement, is exactly where these older software versions are potentially designed to fail catastrophically.
It's a major flaw, and it led directly to one of the study's most critical practical recommendations.
Which is?
Since the error is known to be localized right around that x00 point, the researchers strongly advise engineers using those older symbolic packages to deliberately select the coordinate origin some distance away from the actual loaded area.
So, intentionally offset your grid. Don't put the origin under the load.
Basically, yes. Don't put the mathematically most vulnerable spot right under the physical area you care most about. It's a workaround for a known software bug.
Okay, let's shift gears slightly and summarize the key takeaways here. This whole investigation is, well, it's a powerful cautionary tale, isn't it?
Absolutely.
For anyone relying on symbolic computation, geomechanics, physics, structural engineering, you name it, the tool you trust, the one you pay for to give you algebraic truth, it can be fallible, and that fallibility can be tied just to a version number.
It really underscores the need for vigilance. The study lays out 3 explicit, pretty much non-negotiable best practices if you're doing this kind of analytical work.
Okay, what's number 1?
First, if you have the choice, use the most recent software versions. For Wolfram Mathematica, we know that versions 13.3 and 14.2, and presumably newer ones, are consistent for these critical Boussinesq functions. They pass that basic calculus identity test.
Makes sense. Use the fixed version. But what if you're stuck with an older one? Maybe institutional licenses or something.
Right, that happens. In that case, the second practice becomes absolutely crucial. Always verify your symbolic results yourself.
How? That sounds hard.
Use that same simple test the researchers used. Before you trust the output formula the software gives you, perform that internal check yourself. Take the complex integral expression, split it into a sum of simpler parts, f plus g, integrate them separately, add the results, and compare it to integrating the whole thing at once.
So basically, redo the calculation slightly differently to see if you get the same algebraic answer.
Exactly. It's the diagnostic tool. It will immediately tell you if you're dealing with one of those unstable versions that produces non-equivalent results.
Okay, vigilance and self-checking. And the third point is a clear warning, I gather.
Yes. Avoid relying solely on the analytical outputs from that known failure group versions 8.0, 11.3, 12.3 without doing significant cross-checking or verification. They are proven to sometimes produce mathematically non-equivalent forms of the solution, which, as we saw, could lead to serious misinterpretations, especially about maximum settlement right under the load.
Did the sources mention if the company, Wolfram, acknowledged this specific residuum issue, or did they just sort of fix it quietly in later updates?
The sources mainly focus on the mathematical findings and the implications. They suggest it was corrected through broader improvements to the symbolic engine in those later versions, like 13.3 and 14.2. So the newer versions effectively are the fix. But the study's real value, beyond warning users, is highlighting how this classic problem, the love problem, serves as an excellent benchmark.
A benchmark? You mean for checking other methods, like numerical ones?
Precisely. In the real world, for really complex geometries, we often have to rely on numerical methods like the finite element method, FAM. But numerical solutions always need validation. You need to check them against something you know is exact, an analytical solution. The fact that we now have verified, stable analytical solutions for the love problem from Mathematica versions 13 and 14 onwards, that's incredibly useful. We can use those verified symbolic outputs to make sure our complex FEM models for similar problems are actually giving reliable answers.
Okay, that makes a lot of sense. So this has been a really eye-opening deep dive. We started with this, specific niche 100-year-old mechanics problem, only to find that the very software designed to automate and enforce mathematical laws can subtly, quietly betray the most fundamental rules of calculus. And it depends just on which version you install.
It's a lesson in computational humility, perhaps.
Yeah.
Just because the computer spits out an answer, even a complex formula, doesn't automatically mean it's the only correct algebraic form, or even fundamentally correct in all cases. Verification is key.
Absolutely. And this really raises a much bigger, maybe slightly unsettling question for you, the listener. If basic integration rules, things we learned in first-year calculus, are proving unstable between software releases for these classical, well-understood problems like Boussinesq square, how much hidden discordance, how many subtle mathematical inconsistencies might be lurking in the newer, far more complex computational models we rely on every single day?
Yeah.
Think about fluid dynamic simulations, complex weather forecasting models, financial derivatives, pricing. What analytical or symbolic tools are you using routinely that might be overdue for a basic calculus sanity check? Something to think about.